I hope you having issues with camera size. Can you see the top, which is the heading, and the last line that says C? Okay, so I think I found that sweet point where the camera's pointing at both things at once. So what I'm going to do today is that we're going to finish off some rates of change questions that we didn't get to last time, which is basically these three. Then we'll move on to our new section, which is called related rates, and we'll get started on that today. And in case I forget, which I hope I won't, this is our second week of the batch of 2, and our test would be on a Monday, but something's happening on this Monday, isn't it? So it will be on the Tuesday. So just to tell you, in case you turn up Monday and wonder where everything had gone. Okay, so let's look at what this story is. So essentially, rates of change are that if you find the derivative of something, you are finding the rate of change of that something. So here is a really ugly formula, but it's quite a realistic one as well, which describes the height or the depth, I guess. Okay, the depth of water in a certain place in Canada. And it's in meters and time is in hours. So it's 7 plus 5 of these really ugly combinations. And when you do real data and real models, real formulas, you don't get 2s and 3s very rarely. You tend to get nothing 0.503s and 6.75s. But they're just numbers. They're just like 2 and 3. As far as I'm concerned, they're just 2 and 3. They're just numbers. So don't let the fact that they're ugly distract you from the generic process. So in question 7, the first thing you're going to be asked is find the rate of change. They ask you to find its derivative. So what that's going to tell you is how the tide is rising or falling, the rate at which it's doing it at any given time t. So I've got 7 plus 5 cosines of stuff. So I'll write it up here. The formula for the depth of the water in the harbour is this ugly guy. So don't get distracted. What's that phrase I'm thinking of? Yeah. I can't see the wood from the trees. Don't get distracted by some of these numbers. Right. If I differentiate the number 7, isn't the answer just going to be 0? It's going to have no effect on the derivative. Now that is a nice number, but see if that was the number 1.23456, wouldn't its derivative still be 0, right? Don't get distracted by how ugly the number is. It's just a number. Right, that 5's nice. If you want to differentiate 5 cosine of something, well, you differentiate 5 cosine, you get negative 5 sine of something, which happens to be all of this. So 5 cosine somethings, differentiate it, you get negative 5 sine of somethings, followed by, since it's a chain rule, the derivative of that something. Now, I know that's a really messy group of numbers here. The something is this guy. Now, if I multiply it out or distribute it, I guess, it looks like this. I'm not even going to write that down. It's roughly about 3 or 4. It's about 3 point something. The reason for it is that if I differentiate this, I don't care what this is, because isn't it just a really ugly decimal number? So what I'm getting at is, if I want to differentiate this, don't I really only need to focus on that? And the derivative of that is where the 0.503 came from. So if you're wondering where's that, it's the derivative of all this with respect to t. And then you kind of try and make it pseudo pretty. Well, I can't really see it being that pretty. See if I've got it here, because it's already done. You get that guy times that guy. Does that give us? It gives us negative 2.515, the sine of the ugly guy. And there is the rate at which the water in the harbour is changing at time t. It's negative 2.515, the sign of this ugly guy. And then there's a whole load of questions that come after that, B, C, and D, and they ask you how fast is the tide rising or falling at, let's say, 9 a.m. So if I want to find out what the answer is at 9 a.m., I put 9 in here, and I get this calculation. And you're going to trust me because I just cheated and found out what they said the answer is. If you multiply all of this, you get negative 2.28 to 2 decimal places. So it means at 9 a.m., the water is going down at the rate of about negative 2 meters per hour. So you can imagine you had an hour to spare and you sat there at 9 a.m. and you just watched the tide go down in the harbour, you know, the little marks sometimes I have in it. It would go down by 2 meters in an hour, which is a phenomenal rate, isn't it? Most harbours don't up and down that much.
Excuse me.
Yes.
So you put 9 in there, and I tried this problem. I thought I had to turn it all into minutes so that my T was like minutes or hours, but not in a clock time, like 9.
The formula up here had already fixed the clock time. So when you plug 9 into here, it's taking care of that. That's why the formula looks ugly, but 9 a.m. is now just 9 for T. And that's what makes life easier.
Oh, okay. All right.
Yeah, a second thing you may want to watch out when you're doing these questions, it's a dead easy mistake. I've done it myself a lot of times. Make sure you're in radians, because if you're in degrees, you'll get the wrong number. So if you want to know it at 10, at 12, at 4 p.m., you'd have to put 16 in because it'd be, 16 hours, 100 hours. And that's pretty much that question done. There's about 3 examples. Yeah, B, C, and D. If it's negative, isn't the water going down? If it's positive, then the tide is coming in, I guess. And the water level is increasing. So really ugly number, but the math is the same, whether it's ugly or not. Okay, next fella, question 8. Bacteria. The population of bacteria is tripling every hour, and you start with 300 bacteria. Find a formula N of T for the number of bacteria after T hours. So you're actually going to create the formula. Well, number of bacteria. If you triple the bacteria every hour, 3 to the power of T will take care of that. First hour, it's 3. Second hour, it's 3 times 3. That's 3 squared. Third hour, it's 3 cubed. T hours, it's 3 to the T. And then you stick in the front. 300 times. Why 300? Because you start with 300 bacteria. So that's a very easy population model. The amount you start with times the rate at which it is increasing, in this case it's tripling, to power of T. And that is a valid answer, but that is not the answer that WebAssign was expecting. What WebAssign did is it realized that 300 could be written as 3 times 100, and that 3 could come up and join with that one, and they made that formula out. I'm not quite sure why they're being so nitpicky. Evidently, they thought that was a nicer answer.
T plus 1 in the X?
Yeah, because what we've done is we've taken 3 times 3 to the power of T. That's like 3 to the 1. And when you have the same base and you multiply them together, you add the powers. So that 3 and that 3 to the T became 3 to the T plus 1. Now, I'm not quite sure, as I said, why they did that. I think that's quite a nice looking answer. I don't see why it didn't want it. Now, we're being asked to find in this question the rate of growth after 2.7 hours. Right, keyword here, rate of growth. What do you think I'm going to do to this formula to find rate of growth?
Derive it.
Didn't catch that, Zoe?
Derive it. Take the
Yeah.
first derivative.
Gotcha, you're right. And I don't like that answer. I'm going to use this answer because it's easier in my brain. So if I use this formula, then its derivative, okay. Can you remember that 3 to the power of t has its own derivative formula, right? If you differentiate 3 to the power of t, you get 3 to the power of t. What else do you get? There's an extra number that you add on when you
Isn't
do
it
3.
times t?
Not times t, no. But it is times something. It's times,
1.
that would be for e to the t. It's that guy.
That guy. Ew.
That guy. 3, natural log of 3. Okay, side issue. Come back to that. You get 2 new guys, you should know how to differentiate. Y equals a to the power of t. I guess I should do a to the power of x. There, right, y equals a to the power of x. Its derivative is a to the power of x with an extra ln of a.
Quick question.
Yes.
Is that not a product formula? So it'd be f dash g dash plus f, or yeah,
No, Robin, it won't be a product formula because this isn't 2 things multiplied together. This is a number
the,
raised to power x.
I meant the rate of change.
Oh, this
equation.
here? Wouldn't really need to be because this is a number. You only really should do the product rule when both pieces have a variable in them. So if that was 100t, yeah, that would be a product rule. But because that's just the number 100, you don't need the product rule at all.
Okay.
Right, now, if you accidentally chose the product rule, wouldn't you make that guy f?
Yeah.
Wouldn't 100, right, what's the derivative of 100 going to get you?
0, nothing.
Right, so you'd end up with the right answer. You just be giving yourself a little bit extra work.
Yeah.
So, does anybody then remember the second guy? What is the generic formula for log to the base a of x? What's his derivative? One on the top.
AX over the bottom.
Yep. Anything else? There's another little bit.
Times the natural log of a.
Now, if you times it, it'd be on the top. If you meant there, then I agree with you. Now, look at the difference between the derivative of a to the x and the derivative of the natural log of a of x. It's just like e to the x, right? You get the original function, but you add an extra log n of a at the front. And if you're doing the derivative of a log, you do get a 1 over x, but you notice you get that natural log of a. That natural log of a piece is accounting for the fact that the base is not e. It's not e to the x. It's not log to base e, right? It's log to base to some other number. So back here, 300 times this is 300 times the derivative of 3 then, which is that guy. And if you want to know what the answer is at 2.7, you would just go to your calculator and you'd find out what that ugly mess is. And I'll put a dot, dot, dot there because I didn't actually get round to hitting my own buttons. I guess I should do it. So 300 times the natural log of 3 times 3 to the power of 2.7. In this case, there'd be about, to the nearest whole number, 6,000 bacteria, 6,400. So if you give me a formula and you want to know the rate of change of that thing, what I do is I take whatever this formula is and I differentiate it. And then I plug in whatever T was in the story. In this case, T was 2.7 hours. And then you calculate. Okay.
Excuse me, I had a question on this one.
Yes.
So when I go, if I just stop and I make a chart and I go, I start with 300 bacteria, and then an hour later I go, I got 3 times, so I have 900 bacteria.
Yeah.
If I stick an hour in, I get 403 based on your formula. Or
well, let me see let's see what that
forget
formula
it, forget
gives.
it. I'm adding, and instead of going 300 times T to the power, I was going 300 plus T to the power.
Uh-oh, that would make a difference.
When I worked out my formula, so I will use your formula.
Okay. Right, I want to do a kind of side issue. I'm not sure that we're comfortable yet with logs and powers. So let's do a side issue. 7 to the x, 10 to the x, e to the x. If you want to differentiate 7 to the x, the answer is 7 to the x. Stick a log 7 at the front. You want 10 to the x, its derivative is 10 to the x. Stick a log 10 in the front. E to the x, e to the x, and you stick a log e in the front. Oh, wait a minute, the natural log of e is 1. So that's why e to the x is a special case. You see, you just get e to the x when you differentiate e to the x. Now, if somebody makes your life difficult and does that, you use the chain rule. It's not 7 to the x anymore, it's 7 to the something. So its derivative will be 7 to the something, right, with a natural log of 7 up front, followed by the derivative of that something. And then you tidy it up a little bit. Oops, my L kind of got bent there. And that would be the derivative. So if you want to differentiate 7 to the power of something, it's the natural log of 7 times 7 to the power of something, followed by the derivative of that something. Now, if you want to do some derivatives involving logs, the log to the base 3 of x, what would that give me? Its derivative is 1 over the natural log of 3 of x. If you want to do a more natural log, would be log to the base 10. Its derivative is 1 over the natural log of 10x. And if you want to do log to the base e of x, which is also called ln of x, then its derivative is 1 over the natural log of e times x. But since the natural log of e is 1, you get 1 over x, and that's the guy that we already know about. Do you see the way that the logs and the powers derivatives work? Right, so we're a little bit more comfortable now. You've seen a few more of them. How to find the derivative of log to base 7x or 7 to the power of x, right? Any questions about that? Can we move on? Last question. I am not a business major. Actually, I'm not that interested in business. But did you know that if you have a formula that tells you the cost in dollars to produce X items of whatever it is, and if I give you a formula for it, that you can find a thing called the marginal cost. Evidently in business, the marginal cost is very useful. It's actually the rate of change of this function. So it is C dashed of X. So if you give me any function at all, and you ask for its rate of change, I recognize that as you have just asked me to find its derivative. In this case, 0.0012 x plus 0.04. Just horrible numbers, 2 times that, nothing. And if you want to find the marginal cost when you're producing 130 items, it's 0.0012 times 130 plus 0.04. And someone else has already done that for me, so let me find out what the answer is. And the answer is $20.34. And this is the rate at which the cost is increasing. So that basically just means that that's the cost of the next pair. So if I want to, a next item, I guess. So if I want to go from 130, how much is it going to cost me to make another one of those items? That's what the marginal cost is telling me. And if you want to find out the true cost of the 131 item, that's what that is, right? So if you go 130 and you make another one, you've got 131. The cost of that is about that much. The true cost, well, you've got the cost function here. If you find the cost of producing 131 and you take away the cost of producing 130, doesn't that give you the cost of the 131st item? And if you find that guy and you take that guy away, you're going to find out that the right answer is $20.44, which means that's actually pretty close to doing it. Now, again, if you're not into business, it might not be your thing. But as far as math is concerned, all I'm doing here is finding a derivative at a particular value of X, in this case, 130. And then the interpretation of it is what the people in business realize that is. You might think, why is this formula even necessary? Don't you just, when you produce things, don't you produce them at the same price all the time? Actually, no. Do you know if you're a manufacturer and you're making tins of beans, if you only make, for whatever reason, 100 tins of beans on one day, do you know the cost of one of those tins of beans is extortionately expensive? And the reason for that is, didn't you pay for all the workers to sit about smoking cigarettes or whatever they did? Because they never really produced anything. And so the more you produce of an item, you tend to be able to produce individually, the individual cost goes down. So it's a very common feature in business that essentially says if you can produce more of something, the unit cost will go down. And that's what this guy here is calculating. Are we good? If I switch you all off because I went and talked about business, not science. Because some of you are math people, but some are business. Right. Quick pause. Who is our next guy going to be? Well, the next section is called related rates. And as if we hadn't put enough layers of information onto you, we're going to put one last one. We're going to find the derivative of expressions when the variables involved, so they're going to be more than one variable typically, also change with time t. So suppose I take the formula for the area of a circle. And this is modeling an oil leak. And on a calm ocean, if there's an oil leak, the oil will expand in a roughly circular motion. And the formula for the area of that circle, not surprisingly, because it's on the surface of the sea, is pi r squared. But I tell you that the radius, right, the rate at which this circle is increasing is at the rate of 4 centimeters per second. So what I'm telling you here is that the r is not a fixed number. It's actually a variable, right? It changes with time. Now, if r is changing with time, won't the total area of that oil slick also be changing through time? So you're very often asked to find the rate at which the area is changing with time. And when you've got
Excuse
stories
me.
like this, they're called related rates. Yes, Teresa.
Can you scoot the paper over just a hair? Because I can't see dr dt equals, I don't know what it equals.
There you go.
Right, thank you.
Right. So that's the gist of what we're going to be doing. We are going to be finding derivatives of variables with respect to typically time. So let's suppose this question was, find this rate. Then how do you get it? Well, if I start with the original formula again, dA by dt is the derivative of A with respect to R times the derivative of R with respect to T. Essentially, it's a chain rule formula. It's just written in a way that you might not be familiar with. If you want to find the derivative of A with respect to T, what you can find instead is the derivative of A with respect to R, which is much easier to do because you've got this formula, and then multiply that derivative by this next derivative, the dr by dt. And I know it's not fractions. These are actually derivatives. But in a lot of ways, this notation looks like fractions. And in a lot of ways, this notation behaves very like fractions. If you thought of it that way, can you not see these cancelling out and you're left with dA by dt? Right, it looks very like that. So how do we do it? Well, differentiate this with respect to r, you get that, times dr by dt, which happens to be the number 4, because they're telling me that, and that is a fixed number. And so the answer is 8 pi r. So if I want to know what is the rate at which the area of this oil slick is changing, the answer is 8 pi r. Suppose I told you a little bit more. Find this fella when the radius is, say, 10 centimeters. Then you just take this answer and you evaluate it when the radius is 10. And the answer is 800 pi. And you could turn that into a decimal if you like, but 800 pi is a nice answer. So I'm going to keep it. So far, so good. Try another one. Suppose we do the volume of a sphere. which is that cube. Imagine that's a sphere, because I can't draw spheres very easily. There's a radius. This might be modeling an explosion, right? So if a bomb went up in the atmosphere and it went boom, it could quite well expand like a sphere. And let's suppose that dr by dt is expanding at the rate of 4 kilometers per hour.
Could I go back to the previous one for
Sure.
a second?
Yes,
Is
go
that
for it.
800 or 80?
Is that 800 or 80?
Because it's 8 times
It's
10
now
pi.
it's now 800 because I've changed the
Okay.
question to suit the answer. Yeah, well caught. Right, we're at this guy. So we've got a sphere, it's expanding through time. The volume of a sphere is this thing. Suppose we're being asked to find the rate of change of the velocity with time. Then we calculate dv by dr followed by dr by dt. And if you differentiate this with respect to r, you get 4 pi r squared. And dr by dt, very often, in this case it's a fixed number, you get this. And so if the question was just find the rate of change of volume with time, you could write that formula down. But they very often have a kind of extra piece where they say, find this guy when r equals, I'm picking 10 again, when r equals 10. So it would be dv by dt at 16 pi 10 squared. There, I think I got the right number of zeros this time. And the units, well, since it's a volume and it's kilometers, it would be cubic kilometers per hour. You do not want to be near that thing when it explodes, because that would cause a lot of damage. I believe comets, the worst comets in the world, the worst things to hit the Earth is a comet that explodes above the surface. Because what it would do is it causes the greatest amount of damage, because can you imagine that sphere as it increases? What it does? Well, one of the things that it does is that it pushes air away from it. And the air will be traveling at a steadily increasing velocity. And I don't know if you know the Tunguska forest in Russia. They believe that one of the theories is that that was an exploding comet that exploded above the surface. And it's literally thousands and thousands of acres were all flattened, and the trees were all pointing in the same direction away from a central point. And that's what happens. When that sphere hits the ground and the air goes sideways, it's like the center of an explosion. It goes out like spokes of a wheel. And that's what the tree pattern looked like. A useless piece of information, I thought I'd just tell you. It was kind of interesting for me. So, related rates. You have a function where the variables, in this case a and r, change through time, t. This one was an area one, this was a volume. Any questions about those two examples?
So how did we get the dv over dr for the substitution that we did?
How did we get the dv? Oh, if you differentiate 4/3 pi r cubed with respect to r, right, multiply by the power, reduce the power by 1, you get 4 pi r squared.
Okay.
And then the dr by dt is just a fixed number because they told us in the story it was that number. So the dr by dt part is typically going to be a fixed value. Okay. Now, Let me,
It seems,
Rid-
to me, it just seems like we could just eliminate the whole step there and just do the derivative of the volume and divide it by 4, the dr.
you could.
But that wouldn't work, I guess.
Well, it would in this case, because if you move that down here, you're just going to get the same answer. Well, what do you mean by dv? Oh, you mean this guy here divided by 4? I think that wouldn't work.
No, it wouldn't because of the t.
Yeah, it wouldn't
dr
work.
over t. Okay.
Sounded like it was a good idea, but yeah. Okay, let me go back to this guy. Right, I've got a equals pi r squared. We already know the formula for dA by dt, so I'll just write that down. And the kind of question that I gave you was, let's start again. A is pi r squared. dr by dt is now going to be unknown, but they are going to tell you dA by dt. So imagine you got the same question. We're going to use related rates, but we're going to use it to find dA by dt. And so how would that how would the back to front formula work? Well, you still know what this is. It's still 2 pi r, right? dr by dt, right? Still this guy. But now that guy's 50. And the reason I'm doing this is that your idea came to me that you could actually use the formula to find the rate at which r is increasing with time if you knew the rate at which the area was increasing. That's not normally the direction these questions go, but you could do it that way if the question asked it. So if the question told me this but wanted to know that, there's your answer, that dr by dt would be this. And at any given value of r, well, you could put the r in there and you get a number. Now, the next one. This is question 2. And it says, each side of a square is increasing at the rate of 7 centimeters per second. At what rate is the area of the square increasing? When the area of the square is 49. Okay, let's take it in chunks. You got a square. Since I do not know what the square is because it's changing, we'll make the side of the square x. So the area of this square is a equals x squared. So the first job was actually to create the formula that we're going to work with. So far, so good. We're told that each side of the square is increasing at the rate of 7 centimeters per second. So we're being told there that dx by dt is 7. So the rate of change of area with time is dA by dx followed by dx by dt. If you differentiate this with respect to x, you get 2x. This guy is 7. And so you get the answer 14x. And if they just wanted to know what the formula for the rate of change of area with time, the answer for that is that the formula would be 14x. But they added an extra bit to the story. They want you to find this guy when the area is 49 square centimeters. Now, if I know the area is 49, and I know that the area is x squared, isn't that just another way, oh God, I wish it wasn't that number, of telling me the x is 7 at that point? And that means that the rate at which the area is increasing is 14 times 7, which is the number 98 square centimeters per second. So I've got a square increasing, the sides are increasing at this rate. The area, the rate at which the area is increasing is 14x. I'm then going to find a specific point when A is this guy, which is another way of telling me x is 7. I wish that hadn't been 49. So imagine this question, same thing, but I wanted to know what it was when the area is, say, 100. Then since the area is x squared, isn't that x equals 10? So the rate at which the area would be increasing when the circle is that area, circle the square is that area, is 14x. It's 14 times 10 is 140. That means that I can tell how the area of this expanding square is changing with time. I can find it when x is 7, I can find it when x is 10, I can find it when the area is 49, or when the area is 100, because those are totally interchangeable. If I tell you what the area is, don't you know x? And that's really what we need. Why do we need x? Because this formula had an x in it, and x is what I needed to know. How are we doing? Are we still in there?
So we're saying that the rate of change is a constant. It's 14 times x.
We're saying that the rate of change is a formula using x, because every time x changes, won't that answer 14x be a different number?
Yes.
So the rate of change is changing with the relationship of 14 times whatever x is. So actually the rate of change of the area of this square is increasing. You know, when x is 1, it's only increasing at 14. When x is 10, it's now increasing at the rate of 140. So if anything, this guy is increasing in a kind of linear fashion. It's getting bigger in a linear way.
Okay, I get it.
Which kind of makes sense. You know, if you go from a square that's 7 by 7 to a square that's 8 by 8, don't you increase a lot more than if you take a square that's a 1 by 1 and then it increases to 2 by 2? Right, a little square increasing doesn't increase its area. A big square, if you increase it by one more unit, does increase by a great deal. Okay, get time for one last guy. This would represent the equation of a circle, wouldn't it? The circumference part, right? Suppose we take a circle and we distort it. Suppose I tell you that the x now increases with time at the rate of 2 units, and the y increases with time with 4. And we'd like to, well, actually, I don't need to tell you that one. Let's just tell you that one and ask you to find that one. It's more interesting. The way to tell you everything. Right. So I have x squared plus y squared equals 25. The x is increasing at the rate of 2 units per second. What's the y is going to increase? Well, we have to change plans here. X and y are considered to be functions of t. So I want to differentiate x squared. So what do I get? I get 2x times dx by dt. And I want to differentiate y squared. And I get 2y times dy by dt. And I want to differentiate 25 with respect to t, and I get 0. Now you might be saying, how come that guy became this? Right, here we go. If you do x squared and you differentiate it, if I call this, I know a, you would do that guy times that guy. So differentiate this guy with respect to x is where the 2x is coming from, and then you finish with a dx by dt. That's essentially what's happening here. Right, you can imagine that that's any letter of the alphabet you like, B, C, D, A. You got that. Another way of looking at that is, isn't that kind of like a chain rule? Where x is considered as a something there, right? What would you get if you differentiate something squared? 2 somethings times dx by dt. Now you rearrange this fella. And you get this fella. And you divide both sides by 2y. And then you make it look pretty. And then you forgot that that was 2. There's your formula for calculating the rate at which the y coordinates are changing through time. And it ends up being negative 2x over y. And we have reached the end of our time.